All right, you had your chance. Make sure you push yourself. You're gonna hit the wall, you get stuck, you go, I don't know what to do. That's when you're learning, you get used to it. We all have to go through it every time we learn something new, right? But write out what you know. The more you get used to it, like I play a little guitar and I think, there's no way I can do that. I just do it slowly and try to do it, and eventually I can do it if I put the time in, right? So you can do this. Write the equation. Translate what you see into pictures and math. Magnets, okay? We're going to come in. Remember I said we're going to do a collision? Magnets, and I'm not going to let them touch. So is momentum conserved? Yes, in all collisions and explosions if the objects are free to move. Is energy conserved? Kinetic energy is conserved because it's elastic. So I don't get any losses to jiggling and deformation. So here we go. What happens? If they come in, same mass, same speed, this one's going to get hit. So it's going to stop and turn around. So its momentum will change. It's going to go from, say, whatever you want to call that, positive, to negative. And that's a change. This one's going in negative. It gets hit, it stops, and then goes positive. That's a change. But the total change, well, it's a collision. So the total change is zero. In other words, this one's going to carry momentum that way. This one's going to carry momentum that way. And then when they hit and bounce, what's going to be true? They transferred, right? Now this one got the momentum to your left and this one got the momentum to your right. Was energy conserved? Yes. How do you know? Because they didn't touch, it was elastic. Could you do it? Yeah, because they both have the same speed. I got 1/2 mv squared plus 1/2 mv squared. Now notice, what's the total momentum coming in? It's 0. mv minus mv is 0 momentum coming in. Momentum going out, 0. Negative mv, positive mv, whichever way you call positive. 0. Kinetic energy, 1/2 mv squared plus 1/2 mv squared. Doesn't add to 0, right? So you got 1/2 plus 1/2, 1. So you got mv squared in, and you have that same energy out. Okay, so that worked out nicely. That's cool. What if they stick? Let's go the other extreme. Took the top of the chart over there. Now we're going to stick together. All right, got to get zen on this. Same thing. What's the total momentum coming in? Same speed, opposite direction, total momentum, same mass, is 0, right? But they're going to stick. So how can two objects that are stuck together have 0 momentum? Could they move that way? Could they move that way? What about kinetic energy? 1/2 mv squared plus 1/2 mv squared. Not directional, right? That's a big deal. So somehow momentum and energy are different things. They capture different aspects of it. Here we go. I'll do my best. See if I can nail it. Trying to get the same speed. I overcompensated for left hand. Pretty good. Let's get a little more bold. You can always know, right? Oh, there. They came in at the same speed. I know they did. Why? Because then they must have had a total of 0 momentum, plus and minus, right? Add to 0, because they ended up with 0 momentum. Energy, was it lost, gained? Well, how much kinetic energy do I have? 0. But I had kinetic energy. It's lost in a perfectly inelastic collision. Also, in an inelastic collision, can I ever end up with more energy? Sure, watch. Energy 0. Momentum 0. I release the stored energy, and here is spring energy. It could be chemical energy, right? How much momentum do I have afterwards? 0, because I started with 0 momentum. How much energy? Not 0. There was energy stored in here that I wasn't accounting for, and I end up with more energy from that collision. Cool. So that's interesting. When I have a truly elastic collision and one comes in and hits the other, that's going to stop. It's going to stop dead if I level my track correctly. It just stops, right? But if they hit even a bit, and that's quite a bit. Let's make it elastic. Oh, that's elastic. It's not elastic in the sense, not truly, because it still moves a little bit. And I can see this with the Newton's cradle. Check this out. So if I go like this, and I take one, can we zoom in on that pretty well? And I got one ball coming in. I'm going to release, I'm going to go from potential energy to kinetic, right? And just before, for the collision, just before and just after, momentum is going to be conserved. And these are Billy Boyle's, they're often called elastic collision. Well, are they truly elastic? Let's see. One goes in, MV out, right? So that's cool. Momentum's conserved. Energy is going to be conserved. Same masses, right? Let's check again. Is it truly elastic? Look in the middle. It's starting to jiggle. Besides which, what do you hear? You hear sound. And you know that they're hitting, so there's some jiggling energy. And consequently, these don't stay perfectly stopped. Not because it's a bad design, but because it isn't truly elastic. It's approximately elastic. It's not bad. And so we can do things like 2 in, 2 out. And eventually there's going to be jiggling because movement there because I've lost energy into jiggling. But it's pretty good. 3 in, 3 M's coming in with a V, and 3 out. That's kind of fun. 4 in, stop it. 4 out. So momentum is conserved. Momentum's conserved. Doesn't matter. Elastic, inelastic, perfectly. 5 in. 5 out. I guess that would be elastic. The potential kinetic, and all that stuff, right? But when they hit, some energy is going to jiggling through sound and thermal stuff, right? So interesting. You can actually make these predictions, and it makes a difference. Let's really quickly talk about bouncing. Now, if I'm doing bouncing, I'm going to go. Let me get all that. That's pretty good. If I bounce this guy, I let go. I could throw it. I let it go. Potential energy. I can think energy counting. More kinetic, less potential. More kinetic, less potential. And the bounce energy compresses. That's elastic, isn't it? It's kind of squishy. But is momentum conserved? Well, you'd have to take into account the desk, which is attached to the building, which is attached to the earth. So in the abstract, but not in a useful sense, momentum's not conserved. Momentum is down, and now momentum's up, right? So there's some collision there. But I'd have to use impulse momentum there. What about energy? Well, let's see if it starts up here, and it ended up here. So I started with mg this h, and got mg this h, right? So I lost it. Where did it go? To the jiggling, right? And so different materials will have different kinds of collisions, different amounts of inelasticity. That one just kind of thudded, didn't it? Let's see, with these two, green and blue, which color bounces better? I don't know, I think the blue one, right? Baseball, what about that? No, not so much, right? So we've got this old guy. I think I tried to pop this guy before, right? I'll try it one more time. I think I have a better one. No, that's not going to do it. Oh well, pop. So in general, if you drop a ball, it starts there. It's got potential energy, it goes kinetic, and in that collision, it's going to lose energy. See? Watch closely. Can you see the table there, Travis? Where it hits? Okay. See how much you can measure how much it lost by the mg delta h there. So I don't know where it all went, but I know it lost, right? So here it goes, watch carefully. switched them. Did you catch that before? All right, so it depends, the material. Maybe you want bounciness. Maybe you don't want bounciness. That's engineering. That's cool. That's material science. It's so cool, right? But you need energy and momentum to do a full analysis here. And just work with the basic structure and then put in what you know. Momentum with these free collisions always conserved, right? But if it goes off in 2D, you got to draw your angles and use your sine and cosine and things like that, and break your momentum into x and y parts. Energy doesn't care. These are added energy, right? They both have positive energy, kinetic energy, and they both have positive kinetic energy. It's not a vector, okay? But momentum does have that positive and negative directional sign. And momentum conserved. Energy, not always, and generally not, unless they have a very special kind of situation for an elastic collision. I think we're good. I think, you know what, I think you guys have earned the right to a derivation for the full mechanical work energy theorem, which we can build on, but that's going to come a little later. So practice, practice, practice. Start with the basic energy accounting equation and fill it in as you know, and it'll start clicking. Energy is your favorite tool.